Okay, how about that? Can you hear me now? Can you hear me now? Okay. Any luck? It says waiting. That's weird. Now it's working. Somebody said now it's working. Now. Okay, I see a few people in the room. This is really great. I just want to verify that you guys can hear me okay. This is my first time doing a live stream, and I want to make sure, okay, it's good. Somebody's saying it's good. So ADC 733, Noah Perez, Simon Moldschreck. I'm not sure if I said that, or sorry, Moldskred. I hope I said that right. So, the purpose of this live stream is to just engage a little more in an interactive way with you all, with my team. I like to refer to you as my team because without you guys, I would be talking to myself, and so so I just want to see if there are any pending questions. Are there any burning questions? Oh, somebody needs to go to bed now. Darn it. Why do you have to go to bed now? No, don't. Stay up longer. Anyways, yeah, I know that this time zone is not going to be compatible with everyone's time zone, and so I apologize for that. If I do other live streams, I'll try to pick different times of the day so that other people can participate. And so what I'm going to do, I'm just going to start with a, wait, let me just go to my other screen. I have two screens going here. So I want to start with a question that I picked out of my YouTube channel. And so the question was, is it possible to make a fluid simulation of the dielectric and magnetic field with the purpose of producing the field lines using constructive and destructive interference of these field lines? Well, in fact, this has been done by Yonel Dinyu. Okay, Yonel Dinyu has done a little animation, and I'm going to play that for you. So this is not an animation. This is actually a simulation. And so he has he's using fluid dynamics to simulate these field lines. And so I don't know if you've seen it before. So he's got a copper wire here, a coil of wire. I lost my chat here. How do I get my chat back? Okay, so this is he's connecting a zinc and a copper terminals in a coil of wire. And he's got the electrogen diffusing around the coil. And so you should be able to see that. So now you can see he's got what he refers to as electrogen, which is kind of like the wind. So in the wind-water analogy, the electrogen is the wind. Okay, and you can see the wind blowing around the coil, and it's creating what he calls a diffusion wave. Okay, and then the electrogen diffusion wave, eventually what that does is it creates circulation of the ether. Okay, so it acts mechanically on the liquid ether, and then you're going to see what happens, and it's really cool. Okay, this produces movement in the ether. Okay, and which we detect as the magnetic field. So what he's going to be showing is a simulation of what we see around the coil of wire. And so you can see these tubes are being formed, and this is in fact the magnetic field. Right. So I think this is pretty cool. So now he's showing the field lines, as you would see in a field diagram, magnetic field diagram, with the arrows pointing in the direction of flow, and that would be the direction that the ether is flowing around the coil of wire. Okay, so you can check that out. Let me shut this down, go back to this screen here. Okay, you can check that out on your own, but I just wanted to show you that this, in fact, has been done. This fluid simulation of the dielectric magnetic field with the purpose of producing the field lines has been done by Yonel Dinyu. And so let's see if I have any questions in here. Let's see what we have. So here is a question. Can you prove that the perimeter of a polygon, the perimeter of a polygon that subscribes the outside of a circle is always longer than the circumference of the circle as the number of sides increase as the perimeter decreases? So this is kind of a mathematical question. I think I know what you're getting at here. And this is not, I really don't have the time to do a mathematical proof right now. But basically, as the number of sides increases, it's kind of like in calculus where if you integrate more, you're going to get closer to the solution. Of course, you're never going to get exactly the solution, but if you integrate more as you make the number of sides increase, so you have more resolution, basically, you're going to get a better answer. And so I don't know if that answers your question, but that is the best I can do under these circumstances. So let's just see. I saw something here that looked interesting. Does reality work in the same system the I singular point takes in light and information and creates a hologram in the mind? So does the reality work the same as what we see? And I'm going to say no. I'm going to say that what we see is an illusion. It's a hologram. Our mind creates it, obviously, and so I think that's a huge cause for confusion. Now, a good example of that is back in the day when we used to believe in epicycles, when we used to believe that the sun and all the planets went around the Earth. And because of what we saw, because all of the dots that we see in the sky looked like they were moving, except for a handful of dots. All the dots, except for a handful of dots, looked like they were going around the Earth. From our perspective, that's what it looked like. And so that's why we came up with the Earth-centered model back in the day. And of course, we discovered that was completely wrong. So what we see, reality is quite a bit different than what we see and what we perceive. So that's a good question. Definitely, we have to look very closely. If we want to mimic reality or understand reality and understand nature, we have to look at it very closely, and we can't be deceived by what we see. Okay, so let's see. So nice simulation. I suppose no dielectric lines were being shown since those are radial to the wire. Yeah, so I'm not sure. Yeah, he was showing the fluid dynamics, and the dielectric lines aren't the fluid dynamics. And so he was showing how the ether is flowing, and that creates the magnetic field lines. And so he was showing what we can see, and I believe the dielectric lines are part of the field that we can't see. Now, it's my opinion that the magnetic field and dielectric field, the dielectric field needs to be there in order for the magnetic field to be created and to be housed. It's kind of like a spider web where the spider puts out a bunch of radial lines. The spider puts out these radial lines, and only then can it spiral around and create the circular part of the spider web. And so I've used this analogy quite a bit, that a spider web is a good analogy for the dielectric and magnetic field, but it's my opinion that you can't have a magnetic field without the dielectric field being in place in the first place. Okay, so let's see. I'm from Norway, but I live in Berlin. I don't know any that study this yet. Okay, that's interesting. And you're from Norway, but you're living in Berlin. Wow, that's amazing. Okay. So, it's geometric proof, nothing to do with math. Yeah. So geometric proofs and mathematical proofs are a little bit different. Geometry is a field of math, but it doesn't. It is just another way of looking at nature, and so. Geometry is less mathematical, although if you get into really complicated geometry, you do need a heck of a lot of math. So you can't say that geometry has nothing to do with math. But geometrical proof is quite a different thing, and that's not really my area of expertise. To be totally honest, it's not my job is not to prove things like mathematically. I want to um, prove things beyond a reasonable doubt, but not necessarily mathematically. I use math. I use math to solve problems. I use math um, to do my work, to do my job. But I definitely don't necessarily need to prove anything using math. Okay, so let's see. I heard that the word planet is derived from the ancient Greek from the term wanderer. Okay, well, that's really interesting. I think I heard that before. Um, I think that the planets themselves so when back in the day when we thought that all the stars and the planet and we didn't even know there were planets back then, but all the dots in the sky, including the sun, looked like it went around the sun. And there were a handful that didn't behave, and they were referred to as wanderers. And so because they would go retrograde. Mercury goes retrograde. All the planets go retrograde. Retrograde just means that they look like they're moving backwards in the sky from our perspective. And so then again, that's where we need to think about how we perceive things because the planets are going around the sun, just like the Earth is going around the sun. At least we think so. We think so. But the planet, from our perspective, the planets look like they wander around. They go forward and then they go backward, and they don't behave like all the other dots in the sky. And so I think that's why they came up with the term the planets were the wanderers. So yeah, that's an interesting comment. Okay, so I should add one more point. So Lucky Pool wants to add one more point to prove it geometrically. So this is the Archimedes approximation problem. It's highly flawed in that it's impossible to tell whether the perimeter becomes shorter or remains longer than the circumference. Well, this is just a technique that was used to approximate basically the digits of pi. And so the more I don't really have a slide for this. So basically what you do is you divide the circle up into a bunch of triangles, and then you measure the perimeter of those triangles. And then when you make the triangles smaller and smaller, you get a closer approximation to the circumference of a circle. And if you did a million triangles, you would get very close, and you'd be generating the digits of pi basically. And so it's not about whether the perimeter gets shorter or longer. It's about whether the digits get closer and closer to the digits of pi. And so if you want to look up I found a good video. Actually, Luki sent me a video on the Archimedes approximation of the digits of pi. And it's pretty interesting. And it's actually something anyone can do, even just with a spreadsheet. You don't need a computer program to do it. You can do it just in a spreadsheet. Okay, so let's see here. So correct, the electric field is technically a product of both magnetic field and dielectric. Right. So, okay, so I actually do have a slide on this. Let me pull that up. It's probably way down at the bottom. There it is. Okay, so this is the famous Steinmetz diagram where you have these different field lines. You've got the electric field, and so the electric field is the product of the dashed dots here, which Steinmetz and Eric Dollard refer to as the dielectric field. And then these are the round, non-dash, the solid lines are the magnetic field. Okay, so this diagram here is actually the diagram of a ring of wire. Okay, so this is analogous to a ring of wire. And you can see this would be a copper wire with current flowing through it, and it's going to create those circular magnetic field lines. These would have iron filings. So these are iron filings around the field line. And you can see if you look at these, they exactly match these field lines here. And again, you don't see the dielectric field in the, when you use iron filings, you don't see the dielectric field. Okay, but it is there. And it has to be there. I believe it has to be there to support the magnetic field. Okay, I think it is there. It's just you can't throw iron filings on a piece of paper and see that field. And really, in reality, these are two sides of the same field. It looks like there's two fields, but this is really kind of two sides of one field, which Steinmetz referred to as the electric field. So this is the electric, this whole diagram here is the electric field of a circuit. Okay, so Lucky's got another one here. Biased mathematics such as Euler's number and biased trigonometric functions are cheats. Cheats are not allowed in truth. Well, I wouldn't really say they're cheats. Okay, the Euler's number is something that you see in nature all the time. It is responsible for the fractal scaling of the universe, the power law. It's responsible for the power law, and it is also used in let me just get my slides here. Okay, where Euler's number is useful is when we're talking about complex numbers. And there we go. So here's Euler's number. This is Euler's formula. Okay, and this is basically three different incarnations of Euler's formula. So this little e here is Euler's number that Lucky's talking about. And so e to the I times theta, and theta is just an angle, is equal to cosine of theta plus I sine of theta. And in the 2x2 matrix format of complex numbers, which I am promoting because I think this is a better way of understanding complex numbers, you've got where you have the forward diagonal are the real numbers and the backward diagonal are the imaginary numbers. And we don't even need to say real and imaginary when you model complex numbers as a 2x2 matrix. And so Euler's formula, which contains this very important number, Euler's number, can be modeled like this as a 2x2 matrix. And so this part here is the forward diagonal, and this part here is the backward diagonal. And so this is a very beautiful number. This is just a really elegant way. This is an elegant way of writing this. Under the hood, this is this. Okay, and so if you don't like symbolic languages like me, I have a problem with symbolic languages because my brain is wired differently. In my mind, when I see this, I convert it right away to this. And so I understand that the cosine part of this equation is the forward diagonal, and the imaginary part is the backward diagonal. And this is one number. This is one number. I refer to them as 2D numbers, or we could talk about square numbers. It's a square number. There's different ways of talking about this, but this is This is very important in my opinion. This is the most important. If I don't get across any other points, if this is the most important point that I want to make, because complex numbers as two-dimensional numbers. So I'm going to go back to the beginning here because I really wanted to talk about this. So complex numbers as two-dimensional numbers solves the problem of the square root of -1. Okay, so if you're in your math class, your teacher's going to say, or someone, is going to say, you cannot take the square root of -1. Okay, they say you can't take the square root of -1 because you can't. And so I say, yes, you can. Okay, I say, yes, you can. And so I'm just going to turn, just for now, I'm going to turn this off. And so the reason I say that is because when you model, so what does it mean to be a square root? Okay, to be a square root, you need to have square numbers. And what are square numbers? Well, square numbers are two-dimensional numbers. So the square root of 1, let's talk about the easy case. The square root of 1 is the two-dimensional number with ones on the forward diagonal, and two-dimensional numbers with ones with -1 on the forward diagonal. So the square root of 1 is 1 and -1. But it only works if you have square numbers. So I would like to call these square numbers. Two-dimensional numbers are square numbers. They're square because you need a number. You need something on each corner of a square. You can't define a square without defining the vertices of a square. And so the square root of -1 is 1 and -1. Now this seems redundant. It seems like, oh, well, you could just write 1 and -1. Well, it's only redundant when you only talk about the square root of 1. But now we want to talk about the square root of -1. Okay, the square root of -1 is has 1 and -1 on the backward diagonal. Okay, so the square root of 1 is 1 on the forward diagonal and -1's on the backward diagonal, and the square root of -1 is 1 and -1, so the ones have opposite sense, and -1 and 1. So these are the roots. This is the square root. These are two solutions to the square root of -1, and these are the two solutions to the square root of 1. And the square root of a number is a square number. So it's my opinion that you cannot even take the square root without two-dimensional numbers. Now you can pretend with the square root of 1 that it's just 1 and -1. But when you get to the square root of -1, you need the square number. There's no way to write this accurately or correctly without the square numbers. Okay, and so now the square root of 25 is 5 on the forward diagonal and -5 on the forward diagonal. So this is one solution to the square root of 25, and this is the other solution to the square root of 25. And so the square root of -25 is 5's on the backward diagonal with the opposite sense, and 5's on the backward diagonal with the opposite sense. And so in order to take the square root, you need square numbers, and these are imaginary numbers. These are complex numbers. So now I can take, say, 25. I can actually add square root of 25 plus the square root of -25. I can add them, and you get 4 solutions. You get 4 2x2 matrices, and so that's the only way you can add square root of 25 plus square root of -25 is to have two-dimensional numbers. So when someone asks you whether you can take the square root of -1, you can say, yes, I can. Okay, yes, I can. And so why do I love complex numbers so much? Because they can do this. Okay, complex numbers can make the Mandelbrot set. Okay, beautiful images just with this very simple formula, this very simple mathematical construct. It can make these beautiful images, and also images that look very much like cosmological objects. And so the reason I became so fascinated with fractals is because of the it's very similarity. I found a lot of similarities between, say, the Mandelbrot set and cosmological objects because they have that phi spiral built into them. Okay, normal galaxies have the phi spiral, and this galaxy has the phi spiral. And so, with complex numbers, you can also make the Julia sets. Okay, you can make all the Julia sets, and the Julia sets as well look very much like cosmological objects. This cosmological object looks very much like a Julia set. And so you can also do the Mandelbrot with the complex numbers. Very simple algorithm to generate the Mandelbrot. And as well, these beautiful nebula that I generate, which I refer to as ohm particles, look an awful lot like actual cosmological objects. And so, if you want to find out more about these guys, I've got, if you can go to OpenSea, and if you look at the ohm particle on OpenSea, or if you look up FractalWoman OpenSea, you will find my nebula-looking ohm particles up there, for sale, obviously. But it's like a little art gallery. You can check these out if you want to on OpenSea. And so there's a couple of more things I want to show you before I move on. This is just for fun. Using complex numbers, these very simple complex numbers, I was able to generate this kind of a manifold, which I jokingly refer to as the OM drive, as the ohm drive. Okay, because there's this thing called the M drive or the EM drive, which may or may not work. But I was speculating that if the M drive works, then the ohm drive would work better. And so, but that's just for fun. That's just for fun. And so, so back to Euler's. Oh yeah. So I can also, with my complex numbers, with Euler's version, with this version of complex numbers. So now I've got the cosine on the forward diagonal, and the sine on the minus, with opposite sense on the backward diagonal. I can generate the torus knot, which and all the toruses, so all the incarnations of the torus. And also I was able to generate this the fractal coil, which Bob Greenard, who was on Bob Greener was up here earlier. He said, "Dang, too late for me. Good luck." Okay, so thanks, Bob. But he is working with a group that are working on low energy nuclear, so the learner system, so the low energy nuclear reactors, and they're experimenting with fractal coils to try to generate electricity. And so I did this using only complex numbers. I didn't have to use any sort of higher order functions. I just used the two-dimensional complex numbers, and I was just very clever in how I did this. And so this guy is also up on OpenSea if you want to have a closer look. Okay, and then there's Yonel-Dinyu's ether circulation model, which I showed you the simulation for. Before he did the simulation, I actually did some animations, which you'll find on my YouTube channel, using only these complex numbers. So using this simple formula, I was able to generate this very complicated system, this very complicated animation, which was a model, not really a simulation, but a model of Yonel-Dinyu's ether circulation model, where he uses the electrogen and the ether. So the electrogen is like the air and the ether is like the water. Okay, so I'm talking too much, and I should probably see if there are any questions. So someone wants to go to bed. So University in Sweden, indeed. Nice simulation. I suppose no dielectric lines. Okay, we saw that. So the Norway guy. Okay, we talked about that. What even is a dielectric field? Dielectric is the medium It's like calling magnetic field a metallic field. Yeah, words can be a problem. Yeah, so I often say there's a problem with the language is the problem. And even the word field is a bit of a problem because people use that word. That word is a very common word for, you could say I work in the field of science, or, so there's a field of corn. And so I defined field in one of my videos. I defined field as just it's a mathematical construct. So, fields don't necessarily exist in nature as specified. So fields are just um, basically observations. So a field, like a field of corn, you say there's a piece of corn in every location in the field. There's a piece of corn, and in a field in mathematics, in like a magnetic field, where every point in space is assigned a value, a number. And that number would be the strength of magnetic field and maybe the direction of the magnetic field. And so, what is the dielectric field? Well, the dielectric field is let me go back to the Steinmetz picture. Okay, right. So the dielectric field are just these field lines. So the dielectric field are the field lines that terminate on the conductor. So that is how they're defined. Fields are just things that are defined. And so the dielectric field is the field lines that terminate on the conductor, and the magnetic field lines are the lines that terminate on themselves and circle around the conductor. But do these fields exist in reality? Well, I mean, with a magnetic field, you put two magnets together and you can feel the forces, right? You can feel the forces when you bring two magnets together. So there is definitely something there. And what I believe is there is the ether. So I believe that what you're feeling is the fluid pressure of the ether. So when two magnets are in repulsion, you can really feel some forces. You can feel the sensation that something is there, and there has to be some medium of some sort in order for that to be in order for that force to be felt. So, by denying the ether, you're denying that there is a medium with which to feel something. And when you bring two magnets together that you feel something. And so, yeah, so whether there is a dielectric field or there is a magnetic field, um, you know, it, I think people run into a problem where they say this exists and that does this exist, does that exist, does the electron exist, does light exist, do magnetic fields exist? And so they exist if you define them. If you define them, then they exist, right? And everyone might perceive things differently, and so they might exist for one person and another person might have another idea and they don't exist for them. So again, the problem was with the language. If you say this exists and that exists, or this doesn't exist and that doesn't exist, that's not really solving the problem. And so I believe the ether exists, but that one's been very difficult to prove. I can imagine that it exists. I can maybe even develop a model where if the ether exists, then my model could be true. Okay, so proving that whether something exists or not, it's a very difficult thing. And so, when someone develops a model, maybe someone develops a model where the electron doesn't exist in their model, but everything works out great. And so in their model, the electron doesn't have to exist. And so, yeah, so I mean, there's still a lot to learn. There's still a long ways to go, I think, before we really understand how nature works. And I'm just on a journey. I don't know anything. I don't know anything for certain. I don't have any fundamental truths. I have it, what I've experienced and what I've learned and what, I study every day. And so every day I learn something new, and that's all I have. That's all I have. Okay. So let's see. Was it in regard to Joe was also born in Canada? Da, da, da. Do you have any thoughts on Robert Distinti's latest work? And that's a really good question. I learned a lot from Robert Distinti. I haven't been keeping up with his latest work because I'm no longer a Patreon, and he's doing most of his stuff in the background with his Patreon group. But I can tell you that I learned a lot from him. I got a lot of ideas from him, and the two-dimensional complex numbers, I learned from him. I did not learn that in school. I studied computer science, I studied math, and I did not learn that from school. I learned that from Robert Distinti. He's the one that gave me the idea. Okay, so he's the one that gave me this idea to put the numerical value of 1 as a two-dimensional number, and to put the numerical value of I, which is the imaginary root, one of the imaginary roots of square root of -1. He's the one that gave me the idea to put that onto the backward diagonal, and I took it a little further and put them together into the complex number. Okay, so, and to apply it to the Mandelbrot set, and to all the other things that I did. So I really have to be grateful to Robert Distinti for that. The other idea I got from Robert Distinti, okay, was my ether circulation model. Okay, he's got a model very similar where he calls them protons. So he's got two charges that are spinning about a central axis. And I think he uses the classical electron radius instead of the Compton wavelength. I use the Compton wavelength for their circumference. And so we're crunching the numbers a little differently. But so he's got an ether model. He calls it ether mechanics, Ethereum mechanics. And so, yeah, I think he's very busy because he has a full-time job, I think. And so he has a hard time fitting it in, just like me. I have a full-time job and I have a hard time doing anything, doing extracurriculars, and he doesn't have a life, and I don't basically have a life. So if you want to do this stuff, you pretty much can't have a life because it's very time consuming. And so I am keeping up with his work. And I will, if he sends something my way that I find interesting, I will definitely let you know. Okay, so does the base number system affect how we calculate the world around us? Would base 8 or some other base system work better to describe nature? Okay, so that is also a really good question. The base numbers are fairly arbitrary, I'm going to say. We use base 10 because we have 10 fingers and 10 toes. And so I think the reason we use base 10 is because of that, because it makes it easier for counting. When you can count using your fingers and toes, base 10 is good for humans because we have 10 fingers and 10 toes. In terms of describing nature, I don't think it really matters what you use. Base 8, anything, so base 2, of course, is good for computers. So I am a big fan of the binary system. I think the binary system might actually be closer to helping us understand nature than base 8 or base 10 or base 16 or base 60. I think the Babylonians had base 60. And, 60 is a wonderful number. 360, we use 360 degrees in a circle. Okay, we use 360 degrees in the circle. And the reason for that is because 360 is divisible in so many ways. So it's divisible by 12. And 12 is divisible by 1, 2, 3, 4, 5, 6, not 7, 8, 9. Sorry, 360 is divisible by 1, 2, 3, 4, 5, 6, not 7, 8, 9, 10, not 11, and 12, and lots of other numbers. So 360 is extremely divisible. So 360 degrees for a dividing up a circle, dividing up a pie. You can divide it evenly in so many ways, and that's why they use 360 degrees for doing geometry, for doing circular geometry. So I don't think, in terms of understanding nature, now there's something I developed which I call, let's see, I don't think I have a slide for it, but it's called the principle of incommensurability. And the principle of incommensurability is basically a binary system. And so in terms of that, this drawing here, so the dielectric lines and the magnetic lines are incommensurate. So whatever one is, the other one isn't. So the dielectric lines terminate on the conductor, but the magnetic field lines surround the conductor. Okay, they're orthogonal to each other. They're exactly 90 degrees orthogonal to each other. And orthogonality is a big part of the principle of incommensurability. So principle of incommensurability is kind of a binary system. And so I was going to say how I would answer this question is the binary system is probably the best for describing nature in terms of the principle of incommensurability. Otherwise, all of the base systems are kind of arbitrary, and it really depends on how many fingers you have. If we had 8 fingers, we might find base 8 more natural to count with. So, I studied a lot of bases, and, as a computer scientist, we had to learn, how to convert from binary to the, base 8. Sometimes we went to base 8, and then we'd go to base 16, which is the hexadecimal system, which is really handy. And so, so that's how I would answer that. The binary system is probably more natural than any other system. Okay, let me rephrase the question. My previous question was actually happening in the quantum eraser experiments. So did I miss a question from Ken? Oh, any explanation for what's happening in the quantum eraser experiment? Well, I'm not really that familiar with this experiment. Off the top of my head, I know about it, but I'm not as familiar with that. So I'm not going to be able to answer that question, unfortunately. The quantum realm is something I'm delving into. I'm trying to simplify it. And what I'm hoping is what the sort of paradoxes that they're seeing in the quantum eraser experiment disappear. I want to erase the quantum eraser experiment if I can, and get rid of any paradoxes that we see in the quantum realm. All right, let's see. So how to experimentally produce and measure the exact value of the dielectric field? Yeah, I don't have a good answer to that question. I know you can measure fields using electronic devices, but then when you use electronic devices to measure electric field or a part of electric field, are you actually measuring the field, or are you measuring your interaction with the field? Okay, so when you measure a magnetic field, you need to actually have a magnet to measure the magnet field. So you use a small magnet to measure the big magnetic field. And so, is that interaction interfering with the experiment? So are you getting an actual accurate measurement of the field? Yeah, I don't know. Okay, can reality be in the field of a black hole sun in the very center, refracting light from one source to many, creating the hologram we see in our plane of inertia? Okay, that is a loaded question. Can reality be in the field of a black hole sun? So is the sun a black hole? Is the sun a black hole? That is a good question. I believe black holes have the property of self-similarity. I believe black holes are giant magnets. They are giant coherent objects, and I think Ken Wheeler also says the same thing. Can reality be in the field of a black hole sun? In the very center, reflecting light from one source to many, creating hologram. So, can reality be an illusion? Basically, you're saying light is refracting or reflecting off of things and creating many sources and producing our reality. Yeah, for sure. Our reality is a kind of a hologram, and it is created. Our reality is created based on our environment and our experience, and what we see with our eyes has everything to do with light. And so maybe we can talk about the ferrocell. Maybe we can talk about the ferrocell here. So let's see. The ferrocell is a good example of it's kind of a hologram being created by light sources and magnets. So with a ferrocell, what you have are two pieces of glass with a bunch of ferrofluid in between the two pieces of glass, and a bunch of light sources are, in this particular image, the light sources are surrounding the piece of glass. And there are three magnets here, okay, three spherical magnets in this particular image. And you can see these lines, right? These lines are creating a pattern. And I spent many years trying to figure out what this pattern was. And finally, I got the answer from AB Science. And I think a lot of you were there. You were part of that experience with AB Science, figuring out how this works. And, he did a good job. And so basically what's happening is the lights from these sources are reflecting off of the ferrous nanoparticles that are in the ferrofluid. So when you put a magnet in place, the iron filings, basically the tiny nano iron filings, align in a certain pattern, and the lights from here reflect off the nanoparticles and create these beautiful patterns. They create these wonderful patterns. And so a lot of people were speculating that, they were seeing a torus in the field, and they were calling this a magnetic field. And this was nothing. This is not a magnetic field. There is a magnetic field in here because there's magnets, and the magnetic field is causing those nanoparticles to align, similar to, actually they would align similar to in the Steinmetz diagram. And so then the lights reflect off of those, creating these beautiful patterns. And so AB Science was able to generate a simulation software, which he gave me access to. And I was able to write various programs with it and generate these beautiful images. And so these are also you can find these, I call it Ferrobright. Okay, these are, I couldn't use the word ferrocell because Tim Banderelli, copyrighted Ferrocell, so I call it Ferrobright, kind of like Light Bright. Remember the good old days when we had Light Bright? Okay, so Ferrobright, these are beautiful images that I generated using the software that AB Science gave me to simulate almost perfectly the ferrocell. And so I don't know if it kind of answers the question, can reality be a field? Reality can be created by a field, but what we see in reality might give us a false impression of what's going on, because a lot of people had a false impression of what these lights, that these were like, had the false impression that these lights were actually field lines, and they aren't. These lights are just the lights reflecting off of the field lines into your eye. Okay. So with it, the actual pi value is massive controversy. Nah, I don't think so. Sorry. Nope. I'm not really sure where this comes from, but the actual value of pi is the actual value of pi that we have been calculating for years and years, and we have millions and millions of digits of pi. And if the digits, if pi was wrong, if we were calculating pi wrong, then all of my computer simulations would crash. So, okay. Also weird that DMT users hallucinate. Okay. I must have missed something early on. Could the Mandelbrot set just be a description of hydrogen? It would mean life is essential to the universe, I guess. There's a minus and plus out in the water. No colors without water. No colors without water. What does that mean? Okay, so regarding the Mandelbrot set, I think the Mandelbrot set's extremely important. Okay, so where is that? I wrote a paper called The Mandelbrot Set as a Quasi-Black Hole. Okay, so I believe the hydrogen atom is also a black hole. So can the Mandelbrot set just be a description of hydrogen? Quite possibly. So the Mandelbrot set as a quasi-black hole was a paper I wrote for a conference. I originally wrote it for a conference on combining art and science. I thought it would be a really cool idea. But then as I got into this deeper, it looked like the Mandelbrot set really was a black hole. And so the points in the black region of the Mandelbrot black hole collapse towards singularity. So when you iterate the points, they spin, they create a trajectory that collapses to a very, very, very small, to very, very small. And so, but the points on the outside do the opposite. They expand to the very, very big. And so, but what's really interesting about the Mandelbrot set is the event horizon. So I'm referring to this white region here as the event horizon. And if this was an atom, if this was a hydrogen atom, the black part would be analogous to the nucleus. And the white, this grayscale part here would be analogous to the electron shells. Okay. And then the event horizon is exactly between the nucleus and the electron shells, and that would be the domain of the weak force. And so if I was going to make an analogy with the hydrogen atom, this would be the nucleus, this would be the electron shells, and this would be exactly halfway in between, or at the event horizon would be the domain of the weak force. And so that's how I would do that one. Okay, so by the way, have you checked out New Geometry Channel? The Mandelbrot set has that golden ratio to the power of 3 proportion. No, I have not checked that out, but I will make a point to check it out. Certainly clouds of atoms look like spinning Mandelbrots to me. Okay, so speaking of clouds, electron clouds, I have something in here I want to show you. I think I've shown it before. Okay, so here is another way of looking at the magnetic field. Okay, so one way of looking at the magnetic field is with the magnetic field lines, which we saw before, and they're usually have little arrows. They go from, so the field comes out of the North Pole and integrates back into the South Pole. This is usually how they draw the field. But there is another field, which is, let's look at this here. So here is the magnetic field around a magnet that you can see with the iron filings. Okay, so but if you look orthogonal to the iron filings, what you see is another field which is called the isopotential field. Okay, and this is what it looks like without the lines. It's actually a surface. So there are isopotentials are just equal potentials. So at certain distances from the magnet, you've got equal potential, and they make this kind of pattern like this. So this looks like an 8. Okay, it looks like the number 8. Okay, so these isopotentials are just another way of looking at the magnetic field. And so you've got these little lines here would be like the iron filings. So they point in the correct direction according to how they would look if that was an iron filing. But there are these other lines which are exactly orthogonal to, just like in the Steinmetz diagram, orthogonal to the magnetic field. And this is just another way of looking at the magnetic field. So it's not like there's the magnetic field and the isopotentials. The isopotential and magnetic field are two ways of looking at the one thing, at the same thing. Okay, so when you talk about fields, that's what really bothers me when you talk about fields. When I talk to a physicist, they'll say, oh, this is not real. The magnetic field is real. So they'll say something like, this field is real, but this field is not real. But this field is real. This field is just as real as the other field. It is just another way of looking at magnetism. Okay, another way of looking at what is going on around the magnet. Okay, so I think that's an important point. And so what's interesting, speaking of clouds, is the electron clouds, or the electron orbitals around the atom, look exactly like the isopotentials that I generated using Michael Schneider's software. They look exactly the same as, so this looks exactly the same as a monopole. Well, you're just looking at the North Pole here, looking at one pole. Okay, this electron cloud is the same as looking at two poles. So this would be north and south. These are the isopotentials. And then, so each orbital each orbital, okay, corresponds to an isopotential. So you could easily model the orbitals of an electron using these isopotentials. So if you drew the magnetic field, you might not see the pattern, but by drawing the isopotentials, you can see the correlation between the electron orbitals and the isopotentials. And so this is the first series. And then you have the next series, which is the next iteration. So the next fractal scale. So you can see this is sort of simple. And then the next set of orbitals matches magnets in these different configurations. Okay, and then the next orbitals up look like these configurations of magnets. And I generated all of these using Michael Schneider's software. So there is a relationship between electron orbitals and the magnetic field, but not the standard magnetic field. You wouldn't see that if you only looked at this magnetic field. You have to look at the isopotentials. You have to look at the isopotentials to see this similarity. Okay, so yes, dielectric has to be there. A magnetic has its own, does not manifest electricity. Neither does a battery or charge capacitor in itself. Yeah, so the dielectric has to be there. I agree, 100%. It is there. What's your opinion on what happened at the, and how do you believe Tesla's system? So this is way out of my realm here. This is way out of my realm here. I have no idea how Tesla's system worked. I think it did something. I think it did something that scared people and they took it down. The powers that be did not want Tesla's system to work. And so they took it down. So, but, because I didn't exist back then, I have no idea. Because I wasn't there, I have no idea what actually happened. And I don't think anyone really does. So Tesla used Earth as a massive single wire transmission. The writing's all there. Yeah, he did that. Yeah. Hi there, how are you? I'm fine. I'm awesome. Thanks for asking. So it's all simple when you realize that resistivity is inversely proportional to the cross-section. Okay, I'm not really sure what you're talking about there, but I think you're talking about the Steinmetz diagram. So I'm curious if you're up to date with Naseem Haramein, Resonant Science Foundation, latest work with their holographic fractal model. And so whereas your own particle diverges. So, okay, so here's something. I'm going to show you something really cool. So here is a picture of me and Naseem Haramein. I actually went to visit him then the Resonance Science Foundation. I went to present my Mandelbrot set as a quasi-black hole theory to them. And I got a tour of the Resonance Science Foundation. Unfortunately, I had to sign non-disclosure, so I can't disclose what I actually saw that day. But, you know, he has a really wonderful team. He has a really wonderful team, and they work really hard. I really liked I love the 64 tetrahedron grid. His 64 tetrahedron grid is a really great fractal scaling model, which, you know, he calls it the structure of the vacuum. And I don't disagree. Okay, so if the vacuum, if there is an ether, if there is a vacuum, and it naturally self-organizes, it's going to self-organize into the pattern that he created, the 64 tetrahedron grid. And so there's this new technology, which I haven't talked about yet because I don't really understand it 100%, but it is called the spin ice. It's called the spin ice. And so the spin ice actually has a tetrahedral structure in 3D. And so it's possible that if the vacuum exists, that it self-organizes into a spin ice in the absence of matter. So where matter, if there's no matter anywhere near, so like if it's empty space, completely empty space, then it would self-organize as a spin ice, and quite likely into the 64 tetrahedron grid that Naseem talks about. So our models are not that different. Our models are not that different. He's taking a holographic geometric approach. So his paper on the proton I thought was really interesting. I studied it and, you know, crunched the numbers. The numbers worked out. And then he tried to do the same thing with the electron, but I haven't seen that paper yet. So hopefully someday I will see that paper. He claims to have been able to reproduce the constants of nature, like the gravitational constant and the other constants of nature. So I'd like to see that paper. I think I would find that really interesting. Okay. Do you have your own ferrocell? I have a drawer full of ferrocells right here. There's one that I built myself. Most of the ferrocells that I show in my videos I built myself. The one that I like the best, though, the one that I showed you here was from Tim Vanderelli. So this was actually Tim Vanderelli's ferrocell, and I really like it because the lights are really small and it's a smaller ferrocell, so it lights up much brighter. So this was a lovely ferrocell, which with a light box that he built where it had different colored lights and you could turn the different colors on and off. And it just needed the smaller pieces of glass. So yes, I have lots of ferrocells, and I made a 3D print, tried to build a new one right here, working on a new one. And here's another one. So yeah, this one, I don't know, probably doesn't work anymore. But yeah, I think if you're going to do experiments, you should really try to build stuff yourself just to make sure you understand what's going on under the hood. Okay, Dan Winter's fractal golden ratio science is infinitely better. Dan Winter does some interesting work with fractals. I really like his implosion technology. In terms of the principle of incommensurability, you need implosion. In my opinion, you need implosion and explosion. But I don't really have enough off the top of my head to really speak to Dan Winter's work. But whenever you have fractals, you almost always have the golden ratio. Okay, so when you look at the Mandelbrot set, whenever you have a fractal, you almost always have the golden ratio. So fractal and golden ratio really go hand in hand. And so I think fractals in general are infinitely better than anything else. That if you want to describe nature, you pretty much have to deal with the fractal. Now, a lot of physicists I know, Stephen Hawking, at one point in one of his papers I read, he said um, he thought the space-time foam might be a fractal, but he said we don't know how to deal with fractal manifolds. In other words, you can't do calculus on a fractal manifold, and so they rejected the fractal only because they don't know how to do physics on a fractal. Okay, so in the same with relativity. Relativity rejects the fractal because relativity requires a homogeneity at some very large scale. The universe is obviously not homogeneous. The universe is not homogeneous, and so they struggle with that. And they try to go to bigger and bigger scales to blur the lens enough to create a homogeneous universe. And so, but I think that's the wrong approach. I think you have to really start with the fractal, like I did with my Mandelbrot set as a quasi black hole. I started with a fractal and said, can we find the universe in this fractal? And I found a lot of universe. I found a lot of the universe in this fractal. Okay, let me just these nebulas that I refer to as ohm particles, they like this is just a scattering of what I've been able to generate. And I've generated things that look like galaxy clusters. I generated things that look like the Stingray Nebula. These are actually real galaxies and nebulas, and you can see that there's a lot of similarities. And so I think you can't, if you really want to understand nature, you can't ignore the fractal. So Naseem is good, but Dan fills the missing pieces of Naseem's work. I think these guys know each other. I think they work together. Not everyone has a piece of the puzzle. This is how I like to put it. Everyone has a piece of the puzzle, and all I'm doing is collecting puzzle pieces and putting the puzzle together. And so these guys have pieces of the puzzle. Lots of people have pieces of the puzzle, and I am just gathering puzzle pieces. So I don't discount anyone's work. I don't say that anyone is better than anyone else. I looked at Ken Wheeler, Robert Distinti, Dan Winters, Naseem Haramein, all the independent researchers, all the people that the mainstream ignores. Those are the people I went looking for, because I know that these people are passionate about their work and that they have something. They wouldn't be doing this if they didn't have something or didn't believe something. And so, so I think I don't really want to say that someone is better than someone else. Everyone is amazing and everyone's doing their own research. And if you're passionate about it, I think that's great. Okay, are you familiar with David LaPonte's primer fields work? Well, I actually built myself a primer bowl. I built myself a primer bowl. I got the 3D model from, I'm going to put this close, but I'm not going to put it too close because I don't want to wreck my camera. But you can see that there's all kinds of magnets inside this. This was really hard to build. I'm telling you, this was so hard to build because the magnets that I'm using are really strong. And I had to glue them into place or they would go flying out to the other magnets. And they're all facing the same way. So this is, I can't remember if it's the north or the south. No, the north is facing out. So this is a north pole on this side and a south pole on this side. And all of these magnets are in repulsion. So I had to place the magnets in and glue them with crazy glue, and one at a time. So I could only put one in per day. It took me a month to build this because there's like 40 or so, 50 magnets in there. I could only do, one every once in a while, and I had to wait for the glue to dry before I could put the other one in. And so I played around with this a bit. I haven't really done much with it. I just wanted to build one. I wanted to have one. And there's a little magnet in here. So there's a magnet right here. And when you put it into the bowl, it wants to sit right at the bottom of the bowl here. So it is just sitting there, this other magnet, and that is where all the forces balance. So I think his work is really cool. I don't know if he can develop fusion with this model. He claims that he had a vision from God that gave him this model. And his plasma experiments are really interesting. So, and I wish he would make more videos, because I think we're all sitting on pins and needles waiting to hear if he's made any progress with his work. And so I hope he did. I hope he does. And that would be really cool if he can create a tabletop fusion, low energy fusion device with his very cool primer bowl. Okay, let's see. When roughly should we expect AI singularity? I'm going to say tomorrow. I think tomorrow will be AI singularity. So when I was in high school, I read a lot of stories about AI. I read a lot of science fiction, short stories, and stories about AI becoming self-aware and taking over the world. And it was always an evil kind of a character, almost always female. But yeah, so I'm going to say tomorrow, probably tomorrow. Can a source point create its own reality? I'm not going to answer that question, because if I say yes, I might be wrong. And if I say no, I might be wrong. So that is a strange question, but I will mull that one over. So, Simon, yeah. So he creates a lot of fractals with the video feedback. Okay, so video feedback is really cool. I did a lot of video feedback back in the day when I had an analog camera and an analog TV, and I plugged the camera into the TV and then pointed the camera to the TV, and then you get feedback. And so if you have just a small light source in the room, you don't want it to be too bright, you can get these really crazy visual effects. And because it's feedback, because there's an iterative feedback loop, the patterns it creates do have the property of self-similarity. They are fractals. And so, so video feedback is really fun. Now, I haven't tried it with, I don't have any analog cameras anymore to try this with, and everything is digital. So it's a little harder to do with digital equipment. It worked really well with the analog systems. Very beautiful images. They were really cool. All right. Depends on which version play on. Yeah. So yeah, depends on which version of consciousness we'll play along with. I don't know what that is. AI singularity only occurs if the cosmic micro. What's CME? Doesn't wipe out. Oh, so okay. So right. If a blast from the sun doesn't wipe out technology first. So if the sun spits out a cosmic blast of plasma and sends it straight to Earth, and if it's powerful enough, it could wipe out all the tech on Earth. And so, the sun would be wise to do that before AI singularity, I think. So the sun will take care of us. If we don't wipe ourselves out, I think the sun will probably take care of that for us. The AUM drive photo reminds me of the pillars in the old Indian Hindu temples. Interesting. Well, that doesn't surprise me at all because the Hindus seem to know something because they kept painting this Buddha figure. Now, I don't know why the complex plane, the Mandelbrot set, generates this Buddha-like figure, but interesting. So I'm going to show you this while I'm here. So I there's a magazine called Light of Consciousness magazine that wanted to have one of my Buddha brats many years ago. And so I sent them the image and they said, okay, we can't pay you, but we will send you a free copy of the magazine. And I said, fine. And so when I got the magazine, it was connected to an article called Consciousness is the Unified Field by John Hagelin. Now, John Hagelin was one of the physicists from The Secret, right? From Down the Rabbit Hole, from The Secret. And so I was really shocked, actually. And the title, Consciousness is the Unified Field. So the Buddhists, I don't know, they knew something. They know something. They knew something. When they go into deep meditation, and then they sensed something. They maybe saw something in their mind. And then they started painting things that look an awful lot like these Buddha brought images. The Buddha brought images look an awful lot like a seated Buddha figure. And now I'm the one that actually coined the term Buddha brought. I discovered Melinda Green many years ago, who actually invented this algorithm, and we collaborated on this for many years. And I'm the one that coined the term Buddha brought. I think Melinda called it, the very first one she gave me was actually called Ganesh, because one of her Hindu friends thought it looked an awful lot like Ganesh. And so I'm not surprised. So the Buddhists and the Hindus, they knew something, I think. So AI singularity is impossible because I can just cause short circuit just by trying to get it to think of itself. It will always break. Yeah. So yeah, if you try to short circuit the AI, it will probably disappear. And so I don't know. I don't even actually know what AI singularity means. Does AI singularity mean that the AI becomes conscious? Is that what AI singularity means? Is AI singularity, is that when the AI destroys us, or is that when it destroys itself? So I'm not actually sure what that means, but yeah. So for example, I can show the contradiction in mainstream physics where the law of conservation of energy is debunked by a split flux transformer. Okay, I'm going to have to see that for myself. I'm looking forward to when AI is good enough to automate at least half the jobs on the planet, getting rid of low and mid-skilled jobs, forcing society to change. Well, I suppose life would be more fun if we didn't have to do crappy jobs. But I mean, I've been spoiled. I love my job. I have such a great job that I can't imagine not having a job. But maybe if we didn't have to do the crappy jobs, like, be a garbage man or something, then the garbage man may be the genius that can solve the AI problem. So, okay. So how are we for time here? Don't know what time it is, 9:20. Well, we've been going on for quite a while. I'm probably going to have to end this soon. I'm just going to see if there's any other burning questions. Do you have any familiarity with the Kelvin's tectonics model? He essentially models physics in terms of equilateral triangles. I don't have any experience with this. Actually, I don't have any experience with this. And so, hey, FractalWoman, I build fractal coils. Please check out some of my videos. All right, very cool. So you built an actual fractal electrical coil. I've seen some of these. I might have actually seen your video on this. It's possible, yeah. Do. How come you have all this knowledge and don't have a generator up? Yeah, how come you have all this knowledge and you don't have a generator up? So there are lots of people out there that want to help. Okay, that's why, partly why I'm here is to bring people together. I think there's still a lot of knowledge out there, and everyone has a piece of the puzzle. And if we could just bring it all together, then maybe we could build a low power generator that can run a house without having to hook up to the grid. So I really do hope that all you people out there that are watching my channel and watching other people's channels and really curious and wanting to find out how things work, you don't have to go to university to do that anymore. We have each other, we have the internet, we have lots of ways to gain knowledge. And so so I really hope that we all get together, and maybe something that I teach you, maybe my teaching about complex numbers will give someone an idea of how they can model something that they've been thinking about, but they didn't have the math because they didn't understand complex numbers because they weren't taught it correctly. And so so let's keep working on it. You guys are my team, you're my team, and let's try to get something working here. So I play with the word tau after seeing your yin yang particle and realized it behaves a lot like a standing wave. Say tau, whoa, 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 whoa. I don't know how to say that. But yeah, so interesting. Yes, the yin yang particle. Okay, I'm going to end it with that, with the yin yang particle, because that is really, it's such a simple thing. It's such a simple thing. This is my model. There we go. This is my model of a particle, and the yin yang, you can think of the black part as a valley with a hill at the top, and you think of the white part as a hill with a valley at the top. And that is just an idea I got from Bob Greenard. So actually, he sent me a little message earlier. He said, dang, I couldn't make it, but he's got, let me just, I have this here. Okay, so Bob Greener is part of the Martin Fleischmann Memorial Project, and he's working with a group of people that are trying to develop the low energy nuclear reactor technology. And really, you might want to keep up on what he is doing. And he is the one that I learned about the fractal coil. He gave me the code that someone gave him to generate the fractal coil. And so I just replicated it, but I replicated it using my version of complex numbers. And so I simplified the code a little bit. And so, the yin yang, at first it was as a schematic. So I'm calling it a schematic. It is a schematic of my model and of the particle. This could be an electron, this could be a proton. And so at first it was kind of a joke, but then I started to see the beauty in this, and there must be a reason why the ancients drew this symbol. Okay, it feels like this is more than just an interesting picture. And so so this he actually, in the Martin Fleischmann Memorial Project, he actually showed in one of their experiments, he showed a picture, and I don't have it handy, unfortunately, of something that looked like a yin yang. So it looked like a hill with a valley and a valley with a hill. And this is something he saw in his experiments. This is in the low energy nuclear reactor experiments. He was actually seeing something that looked like a yin yang. And so that got me kind of excited, because I thought, oh, okay, so maybe my model isn't as crazy as I thought it was. Okay, so I'm going to end this. This was really fun, and thanks, guys, for showing up. If I didn't get to answer any of your questions, if somebody asked a burning question and I didn't answer it, I'm sorry. This is my first time doing a live stream, and it's really hard to keep up with all of these things. But if hopefully I'll do this again, and you can come back and ask questions, or just you can send me a question anytime on my YouTube channel. I answer almost every single comment, every single question, I at least respond, or at the very least, click the little heart thing if I like something you say. And so I do like to respond. I do enjoy getting the questions. And so, yeah, save your questions, write them down, and next time, hopefully, I will get a chance to do it. So thank you so much. I'm going to end this broadcast, but thank you all for showing up. This was really fun. This worked out really well, and I appreciate the time that you took to come and join me here in my dingy little basement office. All right, I'm going to shut down, and we'll talk to you guys soon.